What do we specifically need trees? What is the reason of having them?
For example, if you want to store the data and at the same time you want to sort it, keep it sorted, we can use trees, for example, because in the trees we can have binary search tree, which is on the left side it will contain the smaller on the right side.
Okay, good. Okay, that is one type of explanation, but is it only this, or are there any more reasons of having trees? For example,
in what was that? Discrete mathematics, we had an explanation of like networks. For this one as well, it was used.
for example,
For example, there were several networks which were connected to something.
yeah, no, I mean, just keep it general. I mean, don't think as a mathematician. But if you can, of course, I'll be glad to do that. But just try to imagine the case, okay? For example, imagine we've got array, right? Or vector, dynamic array, right? What are the limitations of arrays, and what are the strong points, strengths of arrays?
Well, it is contagious.
Integers, all right.
It is fast.
Fast in terms of what?
In terms of accessing.
Accessing, exactly. But in terms of other operations, it's actually extremely slow, right? And it's very demanding, correct? So because of that, to be able to fix that, we actually try to introduce something that is called linked list, correct? However, linked list, while it was solving a couple of problems like insertions or deletions because of its pointers, and because of having literally more size, right? Then, for example, vector, correct? Because for vector, you must follow the rules of contiguity. But in linked list, you don't need to. Right? Literally, any small part of space is sufficient for you, and you will be controlling all those spaces with use of couple pointers. That's it, correct? So that's really good in terms of that. However, still, this was facing some difficulties and problems. For example, now because all those elements are random nodes, that every node only knows about, let's say, maximum 2 nodes. Okay, for example, the next or the previous one. All right, which means, for example, if you would like to access some of the elements which are not in the very beginning, then you must go one by one to reach that element. Okay. And also another problem is, for instance, now you cannot control each and every node with, for example, its indices. Okay. Even if you do, it's being done with some kind of a, let's say, counter, which is globally allocated or assigned within a class or the type, right? So in any case, now you must, traverse your linked list one by one to be able to reach some specific value, which you do not do in arrays, right? And to fix this, trees have been introduced. Okay, to lower that traversal time, for example, trees have been introduced. This is also another reason why. For example, in linked list, every node only knows about the very next. For example, let's just keep it simple. Let's concentrate on only single linked list. Okay. And in single linked list, every node knows where the next node is. Correct. For example, in tree, however, every node now has 2 pointers for 2 sides. Okay? So at the same time, in linked list, if you were going only one time while traversing, now we have options to go to skip one more. You understand? So if you're somehow trying to reach some level, now instead of doing n operations, you could actually do, for example, log n. So which is quite fast, correct? So in order to, let's say, decrease that access time, these kind of trees are also quite useful. Okay, and of course, because we are now touching the ground of log n, for example, it's also quite handy if we try to construct everything in a, for example, sort of fashion. Right? For example, just like in BSTs, binary search trees. If you're interested about that a lot, for example, you can also apply a similar technique for example, n-ray trees. But in this case, you might have, for example, not only one option like lower or bigger. Maybe your category is contained of multiple subsections, and according to those multiple subsections, you can simply sort the data out. So as you can see, it's not just about numbers being sorted from in ascending order, right, from smaller to larger, or vice versa. But now we can categorize it. You understand? Okay. Maybe you need, for example, odd numbers in a specific fashion, right? So you'll be moving some specific direction with that, for example, right? Do you understand what I mean? So these are very useful. Trees are very useful in many like concepts, like if you can think of. Anyways, now we do all understand about these kinds of data structures. So trees are literally trying to solve, trying to join, let's say, the strength of, for example, arrays, okay, and the strengths of, for example, linked lists in one, so that now we'll have no, let's say, slow paths or any kind of operations we can actually think of, right? All right. So indeed, when it comes to sorting something or categorizing something, if you don't have any kind of data, the best option is a closed trees. There is no better solution so far in computer programming yet, okay, in computer science. But if what you want is, let's say, unsorted data, just random data, then the best approach is not tree, okay? There is a better solution, and that's called hash tables, for example, right? And we have already talked about it, but in the future classes, I'm pretty sure you will have, more in-depth look in hash tables, because that's also very important. Anyway. Now, like we've had a look at this kind of style before, right? For example, if this is regarded as an actual tree, and everything, well, this tree also starts from a seed, right? And seed thereafter becomes a root, correct? But in an actual tree, root is under the ground, while in, for example, computer science, the root comes on the very top, okay? And then you can have, like, different types of children. For example, here, in this link, it's got one child, and this guy has got three children, and etc., right? Okay. So, in general, trees could be different. So, in this course, I decided to go for, mainly binary types of trees, because this is the very beginning. If you do understand what binary trees mean, general types of trees are also not that difficult, actually, okay? So you can simply have a look at them. And also, binary trees are regarded as the most popular ones, and they are the ones that you will be needing the most, okay, in comparison to these. Okay, anyways. Now, in tree, like root is regarded as the very first node that you actually have in a tree. Okay, for example, A is the very beginning tree node, and therefore it is actually called as root. Okay, and the thing that connects, multiple nodes with each other, for example, a parent with a child, is called an edge. Okay, and an edge, you can understand that one as a pointer, for example, in C++, for instance, right? Okay, and parent, for example, is something that can actually have some children. For example, this guy, right? Or you can also understand parent as something like some node which is one level above and is connected with an edge, okay, to the current node. All right. So, for example, this is some current node, and this one is one level above, for example, right? And this is connected with an edge. Okay. All right. Cool. As in child nodes, for example, for the root, this root, children are B and C, while for B and C, children are D, E, F, and G, H respectively, and I and J are the children of E, while G has only one child, like this, okay? And siblings are the ones which have or which share the same parent, okay? So, for example, in here, this parent has 3 children, and now for D, E, and F are siblings, or vice versa, okay? For E, D, and F. For F, E, and D, and etc. Okay? So leaf nodes are the nodes which are the ending nodes, okay? And they do not have any kind of continuation afterwards. And also in here, we introduce leaf nodes as these ones, for example, right? And here, however, leaf nodes are sometimes also regarded some kind of nodes, which are actually new. Okay, so it depends. So don't get confused at all. But in any case, they can be understood as the very ending nodes, or like the end of your trees. Okay, it just depends on the type of, for example, problem you're solving. But in any case, you will first of all be given some instructions for that specific problem. If leaf node is regarded, for example, as null, like the end. All right. Anyways, so internal nodes are the nodes which are not leaf nodes. Okay, literally not root and not leaf and in between. Okay. For example, E is an internal node, B is an internal node, G is an internal node, but not H, not K, not J, not I. Alright? And degree, like you can actually have, let's say, two types of degree. Alright? One is called out degree and the other one in degree. Okay? So for example, the out degree for B is, for example, 3, because B has got 3 children. But in degree for this guy is only 1, because it's connected with a single edge, right? But we'll not be having a look at some too complicated types of trees. That is for the next course. Okay, anyways. The levels are something that you can understand in this fashion. For example, root is at level 0. Whenever root has some children, that is the very next level. So you add all the time for that, like, kind of, what is that? How do you call it? Like, I know vice versa, it's like predecessors, right? Like ancestors, so we can regard that as ancestors. So anyways, these ones are children, grandchildren, okay. Grandchildren, etc. They are known as, whenever you have one grand, it's like 2 levels above, right? So we understand. For example, you start from here, every now and then, whenever you have some children, you will increment the level by 1, for example. And the number of nodes can vary depending on the type of tree you're actually working with. For example, in an n-ary tree, like you might not specifically tell how many exactly nodes you have in one specific level. Okay, it might be different. But in binary tree, for example, you can have up to the powers of 2. Okay? Anyways, so level 2 and etc. So these ones are regarded as leaf nodes, but in some cases, I'm repeating again. Leaf nodes are also regarded as something as, for example, from D you have 2 empty pointers, correct? Null pointers, left and right, correct? And those pointers will be pointing at some null PTR, and those null PTRs can also be regarded as leaf nodes in some cases, okay? So don't be confused, okay? But in a general form, just regard the very ending nodes as leaf nodes, as we are calling them as leaf nodes, okay? If someone wants to mean those null PTRs, then they can also call it as just leaves, okay? Not leaf nodes. Alright? Cool. Alright. As for the height, you start from the lowest level to the top. Okay? For example, now height in here through the specific path is regarded as 3. But for example, depth is the opposite of height. For example, if you start from here and you go down below the root, just like this. Okay? So anyways. Now the paths can be different depending on where you actually start. Okay? And what kind of criteria you're actually following. Okay, for example, you will have some specific rules to be able to get some path, for instance, right? And for that, for example, if you'd like to go from C to K, the only path you can actually reach is through G and then K. Okay? Or for example, if you'd like to go to J, the only path you can go is actually this. Right? Correct? Okay. Cool. Now, a subtree is something through which you can build up another tree, but now a root of this subtree is actually a child of some specific, the actual tree, right? Of some root, or let's say an internal node of that actual tree. Okay? For example, you have A as a root, right? And B as a child. Now, starting from B, you can build up or choose all of it as another subtree. Or for example, starting from this, you can choose all of this as another subtree, right? Anyways, you understand, right? No problems here. So anyways, we've been talking now about trees in general. We did not pay attention to specifically binary trees right now, right? As you could have seen, like there were multiple filters, not only two, or not up to two. But from now on, we'll be paying attention to only binary trees, okay? Specifically to binary search trees. And today, we need to go through a lot of things actually, okay? So I decided to, make them as small as possible. For example, I decided to speak about 3 types of self-balancing trees as well, but really quickly, okay? I'm just going to give you a glimpse of what it is, right? Try to explain why they're important, okay? But the most important thing you need to understand is this one, okay? Because all types of self-balancing trees are actually, types of this guy. Okay, binary search tree is a base, okay? So today we'll mainly be talking about ABL trees, okay? Red, black, and also splay trees, okay? 3 different types of self-balancing trees, and we'll try to see the differences between them, between each other, okay? Now, but before going to those topics, I'd like to ask a couple of things. Why do you think we need to use those kinds of trees? ABL, splay, or let's say, red, black. So I call them self-balancing, right? So if we have a binary search tree, what is the meaning of having them? What is the reason that we need those kinds of algorithms? Whose base is actually a binary search tree. What do you think the purpose of them are or is? So whenever you have a binary search tree, what do you actually do?
Just first complete.
Okay, from here, so left side, right side, to try to sort, right? Okay, cool. But do you remember that binary search trees can actually be built in various fashion, right? For example, if you have some specific data given, correct? Now you can build up literally, multiple versions of that binary search tree, and all of them are possible, right? Right? So, what kind of drawbacks is it going to give to you? Okay, we'll continue. So, this is the general type of tree we've talked about it, but in binary tree, unlike general trees, you can only have up to 2 children. Okay, every time. So in here, for example, would have 3, and this guy has 3, and this one only has 1, and that's okay. But for this guy, it's not like that, right? Cool. Now, representation of binary tree, you all understand how it's actually done, correct? The only thing that, okay, now we can actually fix this, right? So the only thing that is different, or that makes this guy different from the ones that we've been having a look with simply like this, is that this time we've got 2 types of pointers. One is left and the other is right. Okay, this is specific for binary trees known. Okay, not n-ary trees known. Okay, so the n-ary tree might have in here, let's say, another type of data structure used. Okay, for the guy, because its number of children are not limited, so they might be different. Okay. All right. Now, we do understand this kind of representation. For example, if you have a tree like this, A, B, C, D, E, F, and G, right? And we have all of it written like this, A, B, C, D, like first comes A, then B, C, level 1, right? Or breadth first search, correct? So we'll today try to have a look in 3 different versions of writing these ones, okay? 3 different traversals, okay? So we finally need to understand why we specifically need them. And they can also call those kinds of traversals as in-order traversal, okay? Pre-order traversal and post-order traversal, okay? So pre-order can also be regarded as, for example, level or similar to this one. We'll have a look. Anyways, Now, for instance, whenever you have this kind of case, right, you can, for instance, imagine exactly the same tree in computer science, just like this, okay? Like, for example, A having two types of pointers on its, let's say, on its left side and right side, for example, right? Pointing just like that. Or this is another type of representation which is simplified, or let's say equalized to the one we used to have was linked list. Yeah? If you remember in linked list, we have one node, and right after that, a small point or a pointer, which is pointing at another location. But in here, we have the same situation, but just now the left side and right side. Okay? Cool. And whenever you have these kind of triple lines of going like in descending order, then you can understand them as null PTRs. Okay? Cool. So now we need to have a look slightly at complete binary tree, full binary tree, or skewed binary tree, and strictly binary tree, or literally all types of binary trees. Okay? Cool. We can call a tree complete whenever it has all its leaf nodes, for example, leaf nodes, at minimum n minus 1 level. Okay? For example, if we didn't have G in here, it wouldn't be called as complete. You understand? For example, if you remove L, it's also complete. It's fine. Okay? Cool. Full binary tree, however, now it must have all nodes in a perfectly fashion. For example, if we're talking about binary tree, correct? So now, at level, for example, 1, we must have 2 children. At level 2, we must have 4 children. At level 3, we must have 8 children. Exactly. Okay? So the ending level that we are at must have maximum number of nodes possible. Alright? And that is called a full binary tree. Okay? For a complete one, however, in the last level, you can have some nodes, and in the previous level also, you must have all of them. Not all of them complete, actually. No, all of them complete. And minus 1 must be complete for full binary, complete binary. For example, in here, in level 2, we have all of them complete, so we must have it. Okay, but in here, it's okay not to have everything, okay, in the last level. Alright? Cool. So in skewed binary tree, it's one of the worst types of binary trees that we can actually have. For example, like this, right? It's just one-sided, or now it's equivalent to, for example, linked list. Okay? So now, of course, for example, insertion and deletion is super cheap. However, now traversal is n, which is not what we want, correct? Okay. In strictly binary tree, you can either have no children at all or 2 children exactly. So every node must have 2 children or no children at all. Okay, you cannot have only a single child. Just like in here, for example, in complete binary tree, we could have this guy, for example, only 1 child, right? F had only 1 child, for instance, right? But this cannot be called as, for example, strictly binary. You understand? Because F had only 1 child. Okay. Here everything is clear, right? Now I'm going to be asking again, what do you think we need those types of binary trees that we just talked about? ABL, slave tree, and splay, and red-black, for example. These are just some examples for self-balancing binary trees. Could you guess why? Not yet? Okay, why do you think we have these kinds of types for binary trees all the time? What do you think the best scenario in here is? What is the best case? Or let's say normal. Which one is the best case for a binary tree, and why?
I think it totally depends on the date.
Okay, good. But is it good, for example?
As you said, no.
Yeah. So
Because all the data is going only to the left side or to the right
but
side.
is it possible to change this one now? Somehow. Is it possible to build different type of tree, for
From this
example, which would be able to fix this situation?
From this tree?
case, what we could actually do, we could, for example, put B on the top, right? And A smaller than B, so A would be here. A, B, and C. Correct? Possible? You understand? So this way we're kind of fixing the problem that we are actually facing with this guy, correct? So now, every other iteration, whenever we try to insert some data into our binary search tree, right? We of course do follow some rule, right? So right side, if it is large right side, until we find its specific position. So if it keeps being greater, right? We will all the time go to right, and etc. Correct? But what if we're trying to build, a binary search tree, this kind of shape? Maybe it's not in the very beginning. In the very beginning, it was perfect. But after that, we're all the time adding, greater and greater values. Sorted bit. In that case, our binary tree is not really useful, right? So it's getting slower and slower every time. So the use cases of those kinds of trees, as I've told, self-balancing, right? So every other iteration, when you try to insert something, or, for example, delete something, they get to check under their conditions as well, this specific binary search tree, and they try not to have these kind of scenarios at all. Do you understand?
Yeah.
They try to build their trees like at the maximum, like this. Okay? Or like this. They try to make this kind of scenario. Do you understand? Because this is a better scenario. You can build it up. Correct? You can modify your binary tree in this kind of fashion. But now, if you try to go, through each and every node, it's super expensive. Correct? Because there are n nodes, and if you try to go through each and every node, now, why is it any good? Correct? So therefore, we do have some different types of binary search trees, okay, which we can apply for binary inserting and deleting. So that they self-balance every time, every other iteration. Okay? Cool. Okay. So in here, I do believe that you remember how it all worked, correct? Okay, no problems here, no problems here. Make it larger. Let's get code. Okay, yeah, by the way, when can you, for example, determine if a binary tree is regarded as empty? You simply check the root. If root does not contain, let's say if root is null, right, then it's automatically empty. If root is not null, then it at least has one node. Root itself. Okay? Cool. Anyways, now, whenever you try to search for something, the best iterative solution would be something similar to this. Correct? For example, you have a binary tree node. This is the type of your tree. And now you're searching for some specific key within your tree. Correct? For example, now similar to the situation when we used to have this linked list, because we don't want to lose a pointer which is originally pointing at our root, right? We're simply taking a copy of it because this guy will be, modified every other iteration because it will be going through, let's say, path, correct? So for example, in here, while t is not null or null PTR, and t's key is not equal to key, which means we didn't search or we didn't find the key yet, right? We should continue, right? So in here we check if key is smaller than t's key, correct? And in here we have if key is greater or equal, correct, than t's key, right? But for the case of equal, I don't believe that we will enter at all because we are already checking that condition here, correct? So in any case, if the key is greater than t's key, do this, right? Anyways, what does that mean? This is actually following the rules of binary search tree, correct? For example, currently we've got our key and we're checking our key. Now, t is pointing at some specific node. and it does contain some key, correct? Now we're checking both of the keys. If this key that we're searching for is actually smaller than the current node's key, correct? Current node is here, and you have right side and left side, correct? Right side all the time greater nodes, correct? Left side all the time smaller nodes, correct? So now what we're saying is, if the key being entered, we compare these guys together, correct? If this is smaller, which side we should go? Left side, correct? So we go to the left side, and then now this current node, which is T, which was pointing at here, now will be pointing at this guy. And now we check the condition we have in our while loop again, right? And if we are pointing at some specific node, we simply say, is this T pointing at some valid data or null PTR? You understand? If it is null PTR, we don't continue. Okay? Cool. Now let's have a look at some actual example here. For example, now we have this root pointing at the root node, correct? Now this one is regarded as legit. If, for example, we didn't have any kind of pointer pointing at root and pointing at this guy, for example, 5, then how many inaccessible memories we would have? If we have our root modified only one time to the left side, and now there is no pointer pointing at root, how many inaccessible memories we would have?
All the right-sided.
Exactly. So starting from the root, right? So 10, 15, 20, 17, and 30, all of these would have become inaccessible, and they would be, occupying some storage from our memory. Correct? Hopefully, if we have today time, we'll also discuss about the structure that we can actually build on. Okay? Which will also use some recursion operations to be able to make sure that we do not have or leave any kind of inaccessible memory behind us. Okay? Anyways. Now, root, therefore, all the time must be pointing at the root node. Okay? Just like in linked list. Head. If you lose head, it means inaccessible memory. Right? Okay. Cool. So now, because of that reason, we created this guy, T, right? T is just a copy pointer. This is a temporary pointer. Okay, now it's also pointing at 10. Suppose we're searching for 7, right? Now we come in here and say, is T pointing at null PTR? This guy. No, it's pointing at root node, and it's an actual value. Okay, good. This one is true, correct? And we come in here. Is T's key, which is 10, right? Not equal to key? 7. Yes, it's not equal. So we continue. We come inside here, correct? Now, like this, we come inside here. Is key, now this guy is smaller than T's key, which is 10. Correct? Yes, it is smaller. So where we should go? To the left side. Right? Like this. We go to the left side because 7 is smaller than 10. So it must be, if it exists, it must be on the left hand side. So now, for example, if you compare exactly the same situation with linked list, for instance, right? Then you would have to go each and every node one by one. But now we have already skipped all the right side. So we don't have to go through 1, 2, 3, 4 nodes, right? Starting from 15. We don't have to go through them. Correct? So it's a lot more useful already. And it's not just about these. Now we'll be comparing all the time with any or with current, let's say, node we are at. For example, now we went to the left side. Now we come back to the while loop one more time. And this time our T is pointing at 5, not 10. So we continue. Is T pointing at some valid data? Yes, it is. Is T's key not equal to 7? Yes, it's not equal. Okay, we check it. If key is smaller than T's key, which means if 7 is smaller than 5, no, that's not like that. So where we should go? To the right side, correct? Because right side must contain the bigger values than 5. Okay, good. We're at 9 now. We continue one more time and check this condition. Is T pointing at something valid? Yes, it is. Is T's key not equal to key, which is 7? Yes, it's not equal. Okay, good. Now, if key 7 is smaller than T's key, which is 9, yes, it is smaller. In that case, where we should go? To the left side. Next, we come in here, and in the next one we say, is T pointing at something valid? Yes, it is pointing. Now, is t's key, which is 7, not equal to key? No, it is equal. It means we have to stop now. And then we can now simply return this node itself, or a pointer to this node. We're returning a pointer to this node. Okay? It means node is in its own original location. We're just saying, hey, that guy's here. I found it, that's here. We're not returning an index by occupying some 4 bytes of storage, for example. You understand? Or in the best cases, it's 8 actually, because it usually uses on size t, correct? And also, we're just using 2, for example, bytes of storage for that. And also, there is no copy value whatsoever. We don't need to care about reallocation that we usually have in vector, for example, right? So every time capacity gets full, it has to reallocate all the values one by one. Of course, you can apply those semantics, which is a little difficult, but still, this one's developed faster. And a better in terms of memory, saving. Okay? You understand? You understand, right? Okay, good. Now, if we try to search for something that actually exists, for example, 6, we do follow exactly the same route, so it's understandable. Now, look, this is the part which makes it different from the one above. When we were searching for 7, for example, right? In here, this guy failed, right? Because t's key was equal to key, right? And in binary search, if something does not exist, if it is an action tree, not only this kind of tree, but for instance, in linked list as well. If you're asked to return a pointer to a node, if it doesn't exist, then you should return not -1 this time, but no PTR. So in here, look, we're at 7. So this one is valid. So we come in here. It's key, which is 6, smaller than t's key, which is 7. Yes, it is small. So we should go where? To the left side, correct? To the left side. And 7's left is pointing at what? No PTR? Okay.
So, I have a question. Does this mean each leaf is pointing the next, or the right and the left is all the time going to be null PTR?
Yes.
So the end of the tree is all the time null PTR.
Yes. This is how we identify, for example, height and depth as well.
It means that 7 to 17, 30, each of them has
2 as well.
Yeah, like 2 sides, like left
Null
and
PTR.
right. Yeah,
Yes.
both of them will be PTRs.
Yeah, exactly. So whenever we were building up a binary search tree, if you remember, or did I do it in lab? Like whenever you try to build out tree node, for example, we have, for example, in value, right? And then node points at left and right, correct? And you can build up, for example, a constructor. And in your constructor, for example, what you can do, you can say node, right? And inside the braces, you can say int, x or value, something you receive from the user, and then that's it. And while initializing x, right, you initialize it as value. But the next 2 are null PTRs, automatic.
Yeah.
It means, so by default, for each node, we make those 2 pointers pointing at node in the very beginning. And once there is something, we just say, okay, now this guy's left PTR is this one, or this guy's right PTR is this one, and something like that. This is how we identify the end of it. The problem is, whenever you try to, point from null PTR to something, that's already syntax error. Okay, because null PTR is already nowhere.
Yeah.
Okay, logically, right? So therefore, if you have some kind of condition, let it be this one, right? Iterative approach, or let it be, for example, recursive approach. All the time, as your default base case, you anyways have your node being contained with null or null PTR, okay? Because that has to be the ending point. And then you decide what's your purpose. For example, you want to search, you want to go through the left side or the right side, you decide now yourself. But The snow feature must be there all the time as a base condition. Okay? The conditions might be multiple, base conditions might be multiple, but you must have that one all the time. Okay? So anyways. Okay, for the coffee tree, this one is not important. Okay, now a couple of things that we need to pay attention today is that I want to show you how does recursive operation actually works, okay, with binary trees. Okay, so we'll be following up, all these arrows, okay, these edges, with different types of colors. Okay, for example, we'll have 3 types of colors: green, red, and purple. Okay, red means go to the right side. Okay, green means go to the left side, and purple or blue means, I don't know how it will be shown in here, okay, because colors are different. Purple means, for example, now it has traversed that specific node. It has done its job. If you have told, for example, to print it, it has printed. Or if you have told to store it in some data structure, it has stored, it's done this part, and now it's coming back. Okay, because every time you try to call out a function, if you remember, we use tap, right? So every time, because of these recursive calls, we all the time have tap, right? So traversing means this got finished, so now it's coming back to the previous function. So that way we will have a purple color, okay? Or blue, I'm not sure this one. Okay, so now green. So we talked about it. Red line right side, green this one, and purple. Is it purple or blue? Purple. Good. Purple means back. Okay. So now I don't want to make it in here. You want this example or not? Or you want a better example? Okay. Anyways, we'll have a look at this one and at the other ones. Anyway, let's get to the other ones. We have here the design. Hope you want to have a look at yourself, please. There is another one that we have to pay attention. Yeah, copy constructor basically will be using this function. Okay, you understood about the copy information, right? Now we need to understand about the structure. Okay, because this is a very important part. So for the constructor, now we'll be using actually another function called destroy. All right. So whenever you actually try to build up some recursive calls to your specific function, right, you'll be building up some paths in the stack, right? Or do you remember about that root? And I told you if you somehow lose access to that root, right, then all of the storage is inaccessible. So the same happens whenever now you're making some recursive operations and your tree has been created. Now you're traversing it, correct? It's being traversed. But what if you have completed all your job? What do you need to do? Now you should destroy each and every node one by one to have the storage empty out. But you cannot simply say, now I'm finishing up my object. Originally, in any kind of, let's say, programming language, whether it be C++ or anything else, they do have their own default destructors, okay? But the problem of destructors, dynamic memories, or dynamic variables is that they cannot destroy pointers at all. You understand? I mean, they do destroy, but the pointers are just something which are pointing in some valid location, correct? So what can compiler do is to destroy whatever we have now. If we are working with pointer, that is what we have now, correct? If we destroy this pointer, it means those nodes which were, originally had some link through root, that has been destroyed. Now all those elements or nodes are inaccessible. You understand? So that is very dangerous. So when preparing a class, for example, for your home assignment, that's where you could have also had some, negative grading going on if you didn't think about that part. Okay? So whenever you try to build up a class, whether it be perfect, if you have not a good destructor, then I do not regard that one as a good home assignment. Okay? Because you're laying behind a huge waste of memory. For example, if you call out 100 objects and then you use them and your function, that specific function which was calling out 100 objects, is completed. Now all the memory which was being occupied by those 100 objects will still be there while the program is running, which you don't want. Okay? You understand? So that's why we decided to build up some destroy function and we try to destroy root. And how do we do it? So we do it this way. So for our destroy function, we first check if p, okay, p, binary tree is current node, is not equal to no PTR. We try to traverse it until the end. Okay, so now we check. Destroy p, go to the left side. It means left lane, okay? And this one is right lane. So we first go to the very left. Left hand side, left hand side, left hand side, until the left node has both has left child, no PTR. And then it comes back. So it has done its job. It has checked that this one is no PTR. It's back. And now I will go to where? Only. Left, right side. Right side. No PTR? Okay, good. Now I also get deleted. Now P, the current node that I have deleted, is equal to no PTR. Okay, cool. I'm here and I come back and I continue. You understand? Makes sense, right? So I do the same operation for each and every node. You understand? This one makes sure that I'm actually deleting all of these guys. Now let's have a look at some examples, right? For example, suppose our P is pointing at this address, okay? Now we're checking this guy. If P is equal to no PTR? No, it's not equal to no PTR. Okay, go to the left side. Good. Then we're at 5. Now go to what? Go to the right side, correct? Okay, cool. So we're here, we're here. Okay, now this guy is null. Now we come back. This purple, right? This purple. Good. Now we go to the right side. It's left. So it's 9. Now P is not equal to null. We check the left side. Left is null. We go to the right side again. Right is null. And we come back. You see? We delete it. And now it's gone. It's gone. And we have to make it somehow something similar to this guy so that whenever we're checking it out with the other kind of condition, it matches our condition in which we're actually checking this guy like this. So that's why we make it null. You understand? So it was nothing now, and we made it null. Okay? Cool. Now, we come back, and we're at 5. And 5 is also destroyed, because this function is completed. Now, we made this part null as well. Okay, that's null. And now, this part is completed. Now, we come back to 10, right? And from 10, now we were here, right? Left-hand side has finished its job, so it completed its job, so we'll be here. Print function is ended. Now we need to execute this function, correct? So we execute that, we go to the right side this time. And now for this 15, we have to go and check and go to the left side one more time. So left side is null, and etc. And we do similar approaches that we've been doing so far. So that's why it's fast forwarding. This one has become null again. It's completed. Now P is in here, and now P will be deleted itself as well. And now P is pointing at null. That's it.
Why every time we delete, we are initializing P to the null?
Because we don't want to, have this case not pointing anywhere. For example, how do you identify a node is, for example, a leaf node? That it's, for example, children or null PTRs, right? So we want to make sure every time that it's actually pointing at null PTRs, okay? So that we do not go to some garbage location, for example. We have to make sure that it's pointing at node. Okay, we just exactly initialize it to point at node or 0x0. It's safe purpose. Usually, whenever you don't do it, it could also work. But let's not do it. No, it won't work. Yeah, it might not work or it may work. Because it will not all the time be pointing at null PTR. Okay? And if it is not pointing at null PTR, whenever you check for destroy P R lane, right? For the right side. You want to go to the right side. But now if it is not pointing at null PTR, what do? You still have to continue.
But you're not checking for null PTR R lane.
Yeah, I agree. It's just I'm telling you that whenever we try to build this one up, we want to build this one up. We want to make sure that every time this guy is treated as a liquid. That's it. Right now, it doesn't make that much of a difference, but whenever you're actually applying this one to other types of data, it does. It's just, you have to make sure that every other node is regarded as a lift node. And a lift node is something which has its right child and left child as no details. Okay? Right now, in this example, it's true. Like, this might seem to be an overkill, for example. And it's going to work without this one as well, but it's not a really good practice. Okay? Do everyone understand, or just two guys? Okay, please have 10 minutes of break, and then we have some more interesting things coming up.